say you should know that you should have in your little library is called the identity function. And I don't really like the book because they didn't put arrows on their graph. But we're going to add arrows to our graph. And I think there were 2 homework problems yesterday that the middle piece of your graph was this function. It was just the function y equals x, or f of x equals x. A couple days down the road here, we're going to talk about transformations again. But every linear function can be derived from the identity function. You can stretch it, you can shrink it, you can move it up, down, left, or right, and it would all come back to the identity function. I call these the parent functions. So this is your graph. This is your equation. It's just the line f of x equals x. What would the domain of this function be? All real numbers. Every x value is going to be used. It's going to go both directions. What would the range of this function be? All real numbers. Is that true for, well, okay, almost every linear equation? Is that true? Can you give me an example of a linear equation that does not have a domain and range of all real numbers? We've been graphing them a lot on our piecewise functions. A line like this has a domain of all real numbers, but the range is only one number. And if we graph a linear line like this, that's another example. Those are the only 2 examples of lines that wouldn't have a linear line that wouldn't have a domain of all real numbers. So if you see a linear equation, unless it's horizontal or vertical, the domain and range will always be all real numbers because there's nothing that you can't plug into that problem. The book gives you a little bit of info about each one. Again, you don't have to write this down. I just find it interesting. This one's not that interesting, but they call it an interesting fact. It says this is the only function that acts on every real number by leaving it alone. And that's true. No matter what you plug in for x, you get the same thing out for y. It's a very easy xy chart to make. Okay? Sounds pretty easy, right? Moving on. The next function that you should know about. The book calls this the squaring function. I think we should also call it a quadratic function. They call it the squaring function because it has x squared. But I feel like of everything that we've done in Algebra 1 and Algebra 2, we think of it as a quadratic. Many students just want to call it a parabola, and the shape of the graph is a parabola, but if you're naming this, you need to either call it a squaring function or a quadratic function. And again, it's up to you if you actually want to make these points on your graph. I just want to give you the basic shape here. For f of x equals x squared, again, this is the basic function that all other quadratic functions are derived from. Always starts at 0, 0, and it's symmetric with the y-axis, right? It's exactly the same on this side as it is on this side. So we could even say that this is an even function. We talked about that. Section 1, 2, I think. Even function means that whatever you plug in for x, you get the same thing when you plug in negative x. What would the domain of this be? For the domain? You were doing the range. We can jump to that one. Brindley says 0 to infinity. In a quadratic, you always have a maximum or a minimum value depending on if the parabola is opening up or opening down. So your range is always going to be restricted. It's never going to be all real numbers because there's always that starting point, that vertex of the parabola. And for x squared, it always starts at 0 and opens up. But if you move it around, the range can change. What about the domain? All real numbers. There's nowhere where that stops on the x-axis. And I was hoping the piecewise function would kind of help us think about domain a little bit differently. The only time the domain on a piecewise function was not all real numbers was when there was a gap in our graph on the x-axis. There's no gaps here, right? There's no asymptotes. There's nothing where it stops. So the domain is all real numbers. Parabolas and hyperbolas, both of which we talked about last year, here's your interesting fact, used in making flashlights and satellites. So when you say you never use math, if you have satellite at home, you wouldn't have it without math, just so you know. But someone did, and you wouldn't have your TV without it. No, but someone had to learn about it. We got to get some people to go through college and do that, to do satellites. Questions about that? Let's go to the next one. The cubing function, I've always called this the cubic function. Again, both would be acceptable. I talked about this one when we were graphing those rational functions a few sections ago, and I always told you that the middle was either a parabola or that S-shaped graph, which is a cubic function. Again, they don't put their arrows on this. But just like the quadratic function, the cubic function is just y equals x cubed, starts at 0, 0. Want to point out here that this was my example that I gave you of an odd function because it's exactly the opposite. Whatever you plug in on the positive side of the x-axis, you get the exact opposite on the negative side. So we'll throw out here that this is an odd function. What would the domain of this be? All real numbers. Pretty good guess, right? Hopefully it's not a guess, right? Hopefully you know there's no place on that graph where x can't be. You can plug anything you want in for x here. There's no restrictions, there's no jumps, there's no breaks, there's no asymptotes. All real numbers is a good thing to write for the domain. Now remember with the parabola, the range was not all real numbers because we had that higher low point. What about on the cubic function? Do we have a higher low point? This side's going to go up forever, and this side's going to go down forever. So are all the y values going to get used? Last year when we talked about polynomial functions, we talked about even and odd functions. Even functions, arrows always go in the same direction, and they won't have a range of all real numbers because they have a higher low point. But an odd function, the arrows always go in opposite directions, like this or like this, and the range will be all real numbers because it goes in both directions. So again, that's something to think about when you're doing it. If you take calculus next year, we'll talk a lot about this point of inflection. We don't really talk about it much in here. But a point of inflection is where it changes curvature. In calculus, we talk about concavity. We would say this is concave down, and then it changes to concave up. So that's a little interesting fact there. Some calculus for you. There we go. What was that, 3? 7 more to go? Again, the book calls this the reciprocal function, also called the rational function. That's what I call it. Rational function is kind of a generic name for any fraction problem that has an x on top and x on bottom. The reciprocal function, it's called the reciprocal function because it's the reciprocal of x, right? It's the reciprocal of the identity function because it's 1 over x. And I don't know why it didn't make a very good line here, but this should be a nice solid line there. And we did this already, and I know it was a little bit confusing for some people. Then we talked about asymptotes, and hopefully it became a little bit easier. But the reciprocal function will always have an asymptote, and it's always those kind of curved shapes that follow along the asymptotes. This is where we get into the thing where we don't have all real numbers for our domain anymore because we are going to have restrictions here. Domain and range. One way to look at domain and range is look at the function and think about what you aren't allowed to have. Like looking at this, you're like, well, there's definitely a place where it jumps. I couldn't draw this without lifting my pencil up. Look at the function. What are you not allowed to plug into that problem? Your asymptotes will be where your domain is undefined. But if you're not sure where that is, you can just look at this, and you should see I can't plug 0 in there. 0 is where I'm never going to reach. This side's going to keep getting closer and closer. This side's going to keep getting closer and closer, but it's never going to get there. So again, we can write this 2 ways. If you're an interval notation person, you have to write the 2 intervals. You have to say, well, this one's going to go to -infinity up to 0. not including it. And then we skip over 0, so we start back at 0, but we still put a parenthesis. And this side's going to go to infinity. When you're skipping over a number, it's sometimes easier to do set notation, and I just want to show you that because I'm not going to mark it wrong if you do that. X can be everything but 0, and so you can just say all x values such that x does not equal 0, and both of those say the same thing. I like interval notation. I feel like interval notation is used a lot, especially in calculus, so that's why I stick with it. But some people did this on their test, some people did this on the homework quiz, and as long as you get the right number in there, it's right. What about the range? Same thing. We have a vertical and a horizontal asymptote, and that's what Logan was saying. Could we use our asymptotes to help us find domain and range? Wherever your vertical asymptotes are, your domain cannot be. Wherever your horizontal asymptotes are, your range cannot be. Like, those go hand in hand. And I gave you that little rule that said if the numerator degree is less than the denominator, your horizontal asymptote will always be y equals 0. And so we can say the exact same thing. Negative infinity to 0, 0 to infinity, or same thing, just change it to y. Y can be everything but 0. More satellite dishes, Logan. Thanks to this. It's true. The shape of a satellite dish. Oh, guess what? We watched it on the computer last night on NBCSports.com. You can still watch the game. But yeah, my husband was so upset that we couldn't watch the game. But then,
I voiced my opinion on the channel.
but there you go. Just Sunday night football games, and then last night, right?
Sunday night.
You know.
Sunday night football.
No, I'm just saying it's not like it's not every football game. It's except for this week, it's one game a week. I'm 16.
There's only 2 games a week anyone ever watches that.
That's not
Sunday and Monday.
I'm telling you, NBCSports.com. You can watch it online.
I wish I could do that. I was watching ESPN on my phone. Watching your eyes.
I know it's terrible, but who knows what the next channel will be that they lose.
They better fix it.
I called yesterday and tried to get them to change to. I said, can you just give me a different NBC? Like, I don't care if it's not local. Like, give me one out of Georgia. I don't care. I'm like, we just want to watch the football game. And they're like, well, let me check into that. And then they said, I don't think we're allowed to do that. I'm like, I don't care if I don't get my local news. We just want to watch the show. But they wouldn't let me. They said, we can offer you a free sports package for 6 months. That still doesn't give me the Sunday night football game. No, it doesn't. Like, it gave you whatever, that NFL Red Zone. But I don't know if it shows the whole game, if it's the only game. Only when they're in the red zone. So, square root function. Again, these are functions that you should know the shape of. A square root function will always be in the shape of half of a parabola on its side. It's not a full parabola on its side because it would fail the vertical line test. The domain and range of a square root function will never be all real numbers because it starts and stops. It's never going to have every value in it. And you should know that by looking at the equation because you can't have a negative under your square root. I put one of these on the homework quiz and lots of people miss this. So when you're finding the domain of a square root function, we even wrote this out in our notes, all you got to do is say, I can't have anything smaller than 0 in my square root. And so if it's something besides just x, you just set what's under there greater than or equal to 0. But for this one, do you agree it starts right there at 0? Because 0 is as small as I can get. Is 0 included in that? Yes, lots of people think you can't take the square root of 0, but try it on your calculator. You really can. It's 0 to infinity. It's not always going to be going to infinity. We could flip it over and it could be going the other way. And so it could go from negative infinity up So it's just important to know the basic idea there. And then the range depends on where you start with the domain. Whatever you get when you plug in that first domain value, that's where your range starts as well. And this one we get to look at the graph. But if I plug 0 in here, what do I get? 0. And that's where the y values start as well. So the range on this one happens to be exactly the same. But not all square root functions are like that. This is like the parent graph, and then we can do all those transformations. But know the shape, and know that the domain and range is not all real numbers. I know people are going to do this now and not pay attention. But here's the interesting fact about square root functions. Take any positive number and take the square root of it. And keep taking the square root. And eventually, you will always get 1. Try it. It's true. Because eventually it will go to 1. Because you just keep dividing, and you keep dividing over and over again. Eventually, you just divide by the same number. Oh, no, I mean the square root. Yeah. Keep taking the square root over and over again. You can hit, isn't there a way to like store your answer? Don't have to keep writing all those decimals.
Sure.
Absolute value function. We did, actually in algebra 1 you talk about absolute value functions. I don't know if you really graphed them. But in algebra 2 we did talk about absolute value functions, but it was very early on. But again, there's some definite features that you should know about absolute value function. One is it's always a V-shaped function. It's not like a parabola where it's a nice smooth curve. We always have done this with the absolute value bars. Your textbook likes to use the thing that your calculator does, which is ABS, and then X, which just stands for absolute value. So just know that both notations are used in this textbook. This one kind of looks like a parabola, except for it's pointed instead of rounded, so you should be able to kind of relate that back to the domain and range of the quadratic function. What's the domain of this going to be? All real numbers, just like a parabola. This side is going to go out forever and give you every positive x. This side's going to go back forever and give you every negative x. So we are going to get all real numbers. But also, just like a parabola, the range is not going to be all real numbers because the range is going to stop or start every time depending on which way that's opening. And for this one, it starts right there at 0. And so we're going to say from 0 to infinity. But again, that can move around. And again, this is, except for piecewise functions when they're kind of jagged when you do each piece, this is the only function that we talk about that's not a smooth curve. I'm always pretty strict when it comes to graphing, especially when we graph trig functions, about you don't make graphs pointy. You need to make smooth curves. This is the one exception to that. It's the only graph that has a corner on it. Okay? Moving on. Oh, look, our friend, the greatest integer function. In general, they're called step functions. That one specific one that we did where you always round down is called the greatest integer function. Yeah, right over there. Again, the worksheet that we did used the notation like the brackets. Your textbook is always going to use the INT. I'm guessing maybe there's a button on a calculator, or maybe some calculators that does the greatest integer. I don't know. I've never graphed the greatest integer function. But that's what they use it. But remember that that's the same as writing it as the brackets. We just did this, so I'm not going to talk a huge amount about it, but remember that you always round down to the next lowest integer, and that's why you get those steps. And what's the domain of the greatest integer function always going to be? looks like maybe that we're skipping some numbers here, but we're actually not. We pick every number between each x value, right? Everyone is picked. So the domain is always all real numbers. But remember that the range is never going to be all real numbers, because that's the idea with the greatest integer function, is you only get integers out of that. So this is one I don't know how to write interval notation. We're going to say y is an integer. Again, think about the ones we just graphed on the homework we went over yesterday. The domain's never going to change, but the range can, depending on what's happening. Sometimes we have just even integers, sometimes we have multiples of 3, and so the range can change depending on what's happening to that problem. And again, they talk about that these have jump discontinuities at every step. And in general, these are called step functions, but this would be called a greatest integer function. How many is that? Pretty much. I have a couple examples. Plus homework. Doing different things with them. Exponential function. Again, we talked about this last year. It's been a while. In chapter 3, we'll go over exponential and logarithmic functions again. But if you see a function where one side is getting smaller and smaller, like a horizontal asymptote, and the other side's going up, you should recognize that that's an exponential function. This one they're talking about specifically e to the x. And remember, e is a number just like pi that goes on forever. It just doesn't get as much attention as pi. But it's actually used a lot. Again, when you're looking at domain, the domain of e to the x never changes. You can plug whatever you want in there for x. And if you look at this graph, this is going to go on forever this way. This is going to go on forever up. And every x value is going to be used in there. So although it definitely doesn't have every y value used, the domain here is all real number. And that's true for every exponential function. The domain is all real numbers. The range is not going to be all real numbers, because no matter what you plug in there for x, when you take a number to an exponent, you're never going to get a negative out of that. You're actually never even going to get 0 out of that. Like, there's no number you could plug in there for x that you could get 0 out of that. And so that's our horizontal asymptote. And so our range is going to be not including 0 to infinity. Interesting fact, I kind of already told you, that it's a number like pi. Leonard looks like Euler, but it's really Euler. He's who you can think. I think it's called E because he wanted to use his initial. Okay? When you talk about exponential, you also have to talk about the inverse of an exponential function, which is called a logarithmic function. And again, specifically, we're going to talk about the natural logarithmic function. Again, we talked about this last year. I think it was chapter 8. We'll do it again this year. And when we get into that chapter, we'll talk about why they are inverses. One definition of an inverse is the domain and range switches. So you're going to see here when we write our domain and range, it's exactly switched from an exponential function. Instead of going up forever, right, the exponential went like this. This one goes down, and then it goes out, and it's going to eventually keep getting higher and higher and higher. And remember, natural logarithm, we write that as ln of x. We like e and ln because we have buttons on our calculator that do those. And the domain and range are switched here. So on the last one, on the e function, the domain was all real numbers. On this one, the range is going to be all real numbers, because this side's going to go down forever, this side's going to go out forever, and eventually get taller and taller. So the range is all real numbers. And instead of having a horizontal asymptote, we have a vertical asymptote on this one. You cannot take the natural log of 0. You cannot take the natural log of a negative number. And so you never can get those negative values. And so it's the exact opposite of an exponential function. I think this is my favorite interesting fact that the book gives us. It says if the x and y axis were both scaled with unit lengths of 1 inch, you'd have to travel more than 2.5 miles along the x-axis just to get 1 foot above the y-axis, because this goes very, very slowly. Like it's going to take a really long time for that actually to go all the way up to the y-axis. So, element of x. Vague memories of that? Is that 9? The logistic function, and this is probably one that you've talked about in biology more than you've talked about in math class. We don't really do a lot with the logistic function, except for every now and again we have a story problem with it. But I think it's important to look at and understand, and then when you see it in biology class or take a science class, you'll be like, oh yeah, I kind of remember that. You can kind of relate it to math. The logistic function is 1 over 1 plus e to the negative x. Again, you don't have to make a lot of points on your graph here. The big thing is that there's an asymptote up here at y equals 1 and at y equals 0. And then it kind of just goes through here. It's kind of like a S sort of sideways. The domain on this, again, if you have e to the x in your problem, you can have whatever you want in there. You can plug whatever number you want in there for x. And if you look at this side's going to go to the left forever, this side's going to go to the right forever. So our domain is all real numbers. For this particular one, the range is very small. It starts here on the y equals 0, and it stops here at 1. And it doesn't include either one of those because those are asymptotes. So the range for this is actually just 0 to 1, not including it. Depending on this problem, that can be very different. This is used in science a lot, talking about like population growth, because although it should get bigger and bigger and bigger, you have what's called carrying capacity, right? You talked about that maybe? That like the environment can only handle so much. That's the top asymptote. Like that's when your population levels off because the environment or whatever can't handle that much. The asymptote at the bottom is you can't have a negative population. And so that's why you have an asymptote at the bottom. Carrying capacity is your asymptote at the top. Look, math and science, they're best friends. And that's what it says. There are 2 horizontal asymptotes. Provides a model for many applications in biology and business. So that's it. That's 10. So now let's graph some. Different versions. I have a piecewise function here, but we're going to skip that one first. We only have like 6 minutes left. And we just did piecewise yesterday, and I feel like we'll be good with piecewise. So let's make this number 1. Part of your homework today, the directions say to use a graphing calculator, but I want you to practice graphing these without a graphing calculator. And it kind of leads us into transformations a little bit. So this says graph f of x equals x plus 3 squared and give the domain and range. And what I really want you to think about when you're doing these is which of the 10 functions does this match up to? What shape should it be when you're doing it? And that's kind of the idea of if you know those 10 functions, you're going to make at least the right shape when you make this. Oh, I heard someone say parabola. How do you know it's going to be a parabola? It's a quadratic. If you FOIL that out, you're going to get x squared. Today, maybe the best idea is to maybe just make an xy chart. And maybe as you're doing these, you might some stuff about transformations might come back to you. You can pick whatever numbers you want. I don't want to graph giant numbers on my graph if I can keep from it. So I'm going to pick numbers that give me pretty small numbers. I have to add 3 and then square it. So keep that in mind. Like you could pick 0, but you're going to get 9 for your y value. So I don't really want to pick 0. What about if I pick -3? Would that be a good point? So kind of think about that as you're doing them. Don't just always pick 0, 1, 2. If I pick negative 3, I'm going to get 0 squared, which is just 0. And I'm going to kind of stick around those numbers. If I pick negative 2, what am I going to get? I'm going to get 1 squared, which is 1. And if I pick negative 1, negative 1 plus 3, 2 squared, which is 4. I think it was Logan, I don't really know who said it, said this was going to be a parabola. It looks like I'm going in the right direction. As I'm picking my x values, my y values are getting bigger. I need that parabola shape though, so maybe make a little graph here and see what happens. Maybe you already know what you need to pick, but maybe not. Negative 3, 0, negative 2, 1, negative 1, 4. Does that look like part of a parabola? I connected these. That's like going to keep going up. Maybe we should pick one more point to kind of see what's happening on the other side. Like, what if I picked negative 4? What would I get? Only the bell rings. I'd get 1. With a parabola, what you want to happen? You want to get the same number, because it should be the same on both sides of that vertex. If I pick negative 4, I get 1, right? If I pick negative 5, I'm going to get 4 again. So by knowing that it's a parabola and knowing that if I can find that point, that vertex, then I can flip it over, that makes things a lot easier. What's my domain of this? All real numbers. What's my range of this? Last year with transformations, we learned that a number inside the function, so a number added or subtracted into the x before you square it, is always going to move that left or right. And so that's kind of where we're going with this, is the transformations. So again, on your homework today, this is on your assignment sheet. A lot of these are answering questions about which of the functions have a domain of all real numbers. Which of the functions are even functions? Which of the functions are odd functions? Stuff like that is what's a lot of this, like the 5 through 16, a lot of that's just writing the functions or matching it to a picture of a graph. And then 23, 24, and going through the rest of those, some of those are just talking about the graphs, some of those are actually graphing. The directions say do with the graphing calculator, but I want you to do those without a graphing calculator. So even if you have one, I want you to try to graph those by hand, and we'll talk about where we are with those tomorrow. Okay?